I'm happy to, it's my pleasure to welcome everyone to the new series of the Fields Number Theory seminar, and it's our pleasure to have Shivani Goel. I hope I'm pronouncing the last name correctly, Shivani.
Yes, correct.
Yeah, okay. From IIIT-Delhi. And she will speak for us on the Hardy Littlewood three-tuple prime conjecture and convolutions of Ramanujan sums.
Thank you, Professor Payman, for the introduction, and thank you, Asif, for inviting me. So today I'm going to speak on the Hardy Littlewood conjecture and give a heuristic proof of the conjecture, three-tuple conjecture, using the convolution theory of Ramanujan sums. So it's a joint work with my PhD advisor, Dr. Sneha Chobe, and Professor Ramurthy. So I'll start with the twin prime conjecture. So for a prime P, if P plus 2 or P minus 2 is also a prime, then we call P to be a twin prime, and the pair P and P plus minus 2 to be a twin prime pair. So we have many twin primes pair, like 3 and 5 is a twin prime pair, 11, 13 is a twin prime pair, 41 and 43 is a twin prime pair. So the twin prime conjecture says that there are infinitely many twin primes, or there are infinitely many twin primes pair. So this is the twin prime conjecture. In 1922, Hardy and Littlewood generalize this twin prime conjecture for any arbitrary k tuples. They get the intuition of this conjecture while they were working on the circle method. So the conjecture says that if we take any tuple, k tuples, d1, d2, dk, and we denote the number of distinct residue class of these k numbers, modulo any prime p by bp. So if bp is less than p, then the number of integers such that the number of integer up to x such that all n plus di are primes is asymptotic to some constant times x upon log x to the power k, and the constant depends on this bp. Bp is a distinct residue class of di's modulo prime p, and the constant depends on b. So they gave the explicit value of the constant. So basically, it's also a generalization of twin prime conjecture when we take two integers. So this is the conjecture. And since we give the heuristic proof using the Ramanujan sum, so I would like to recall the Ramanujan sum. So if we fix an integer, if we take the positive integer q and n, then the Ramanujan sum is basically sum of all nth power of qs primitive root of unity. So this, sorry. E to the power 2 pi I j. If j and q are co-prime, it's just the root of unity, qth root of unity, and we take the nth power of it. And surprisingly, we can write this sum in a simpler form in terms of Mobius function. So which is if d is a common divisor of n and q both, it's the sum of over the divisors time d times mu q over d. And from here we can see that it's a integer valued function, and since it's a convolution of two multiplicative function. So it's a multiplicative function when we take n to be a constant and take the summation over q. So Ramanujan got the intuition of Ramanujan was trying to find the series expansion of some arithmetical function, and he wrote the many arithmetical function as a series expansion of Ramanujan sums. And there are many applications of Ramanujan sums. We can use the Ramanujan sums in the cyclotomic field. Ramanujan sums is also used in the signal processing, in algebra and in number theory. There are many applications of Ramanujan sums. Also, from here we can see that if Q is a prime P, then if P divides N is just the inner sum is 1, and we have Euler-Phi function. And if P does not divide N, is a summation of all primitive roots of unity, kth primitive roots of unity, which is always -1. So we will use this later in the proof. So what is the idea? Like, first I would give a brief sketch how we connect the Hardy Littlewood conjecture with the Ramanujan sums. So basically, when we take the Born-Manglot function, which is log p, when n is some prime to the power k, and it is 0 otherwise, so we can see that it's the best approximation of prime numbers. So we can write Hardy Littlewood conjecture in terms of Born-Manglot function, which is the summation of Born-Manglot function over n is congruent to constant, the same constant times x. Now, instead, like, we need to show that the sum is asymptotic to this, and from the simple calculation, we can see that these two sums are asymptotic. So like, it's very simple. We can see so we know that lambda n is log p when n is some time to the power k, otherwise it is equal to 0. So we can consider n plus d1, n plus d2 all to be some p1 to the power k1 up to pk to the power, say r1, rk. And this phi n upon n is nothing but p divides n plus di 1 minus 1 upon p. So if n plus p1 is some p1 to the power r1, then this pn plus t1 upon n plus t1 is 1 minus 1 upon p1. And similarly, we can find all the sum. So if we take the first, if we take the difference of these two sums, then and for the first we have like 1 minus 1 upon p1, 1 minus 1 upon p2, 1 minus 1 upon pr times log p1, log p2, log pk, sorry, pk. Then the first, when we take the first component, the log term will get cancelled from the first summation, and we get only 1 upon p, the big of 1 upon pi times log of p1, log of p2, log of pk, and summation over n, which is a big of log of x to the power k times log x. So from there we can see that these two sums are asymptotic. Now, as I told before, Ramanujan gave the series expansion of many arithmetical functions in terms of Ramanujan sums. So Hardy gave a formula of Born-Manglot function as a series expansion of Ramanujan sums, which is like, instead of Born-Manglot function, he gave the series expansion of phi n lambda n over n, where phi n is the Euler-Quotient function, and the summation is over q's, and is fixed. It is phi q mu q upon pq times cq of n. And if we see here, in the inner sum, we have the same function, which is the Hardy give the formula. So we are just substituting the Hardy's formula. We are substituting Hardy's formula here and writing the prime tuple conjecture in terms of Ramanujan. So, so the Hardy formula gives this: the summation over Qi's mu q1 up to mu qk divided by phi q1 upon phi qk times the summation over Ramanujan. And since these sums are independent of time, we can take the summation inside. Now, since this series is not absolutely convergent, so this is not an exact formula. This is a heuristic way to solve the k-tuple conjecture. And so, if we see this sum is independent of x, so if we find this limit, limit 1 by x, if we say that if we divide the left sum, this sum by x and take the limit and show that it is equal to the this absolutely constant, then we are done. So for that we need to find the convolution of Ramanujan sums. So that's the problem comes to the Ramanujan sums. Now, so Carmichael in 1932 give the orthogonality property of Ramanujan sums. So he proved that the convolution of two Ramanujan sum is CR of H when R is equal to S. Otherwise, it is equal to 0. So they like he did the problem independently. He was not thinking about the Hardy Littlewood conjecture. He was just trying to find the properties of Ramanujan sums. So the proof is very simple. So if we substitute the definition of Ramanujan sums, which is the sum of primitive roots, we can write this convolution in exponential sum. And now we see that inner sum, like we can have a upon r plus b upon r to be an integer or not to be an integer. So if a upon r plus b upon s is not an integer, then this sum is bounded. And when we take the limit 1 by x, it goes to 0. So the sum is 0. So for a non-zero value, we this a upon r plus b upon s has to be an integer, which gives us r is equal to s. And when r is equal to s, this sum is bounded by the x, and this limit goes to 1 by x, and we have just the Ramanujan sum CR of H. And using the Carmichael result in 1999, Gadia and Padma give a heuristic proof of Hardy Littlewood conjecture for k is equal to 2. They just substitute the value of Carmichael result here and show that the limit is equal to this constant. So this is a simple proof. So our aim is to find the result for k is equal to 3. So for that we need to find the triple convolution of Ramanujan sums. So we use the definition of Ramanujan sums and write the sum in exponential sum. Now, similar to the case k is equal to 2, if this fraction a upon r plus b upon x plus c upon t is not an integer, this sum is bounded. And when this sum is bounded, when we take the limit 1 by x, this goes to 0. So we need to consider only the cases when A upon R plus B upon S plus C upon T is not is an integer. So the problem converted to the cases when this fraction term is an integer. So we consider different cases. The first case is when R is equal to S is equal to T. In that case, this fraction is an integer, implies A plus B plus C is congruent to 0 mod R. And since we know that A and R are co-primed, it implies B plus C has to be co-prime to R. So this gives the limit of the convolution is equal to summation over R over B and C, such that B is co-prime to R, C is co-prime to R, and from there B plus C is co-prime to R, and this exponential term e to the power 2 pi I HB plus JC divided by R. Now this term looks like Ramanujan sums if we consider the two variables instead of one variable n. And although this sum satisfies the similar property as Ramanujan sums, like this sum satisfy the orthogonality property, which is proved by Carmichael for Ramanujan sums. So we call this sum to be a two variable variant of Ramanujan sums and denote it by curly sub R of H and J. Similarly, like we know that CQN is the multiplicative function of Q when we fix N. Similarly, if we fix H and J, this two variable variant is a multiplicative function of R. Also, if we take R to be a prime.
So that's not obvious, right? Because you have additive condition of
yes.
So there's some work that's needed.
Yes. To show that this is multiplicative, we need to take like some work. We need it's not okay. But yeah, it's a multiplicative function. But this is obvious. So if R is a prime, then so B plus C is not co-prime to R if and only if B is congruent to minus C in mod R, and which will give us this CPH minus J. Otherwise, it is always co-prime to R, and so we can write it is the product of Ramanujan sums to Ramanujan sum minus the case when this is not co-prime to R. So we'll use this later. Now, since our problem is on the
The second thing looks almost like a kind of additive version of Boosterman's. Because
yeah.
you're doing but the relationship between the multiplicative inverse. Yeah, you want an added kind not exactly, kind of an additive.
So if like in Klosterman sum, H and J are in like H is co-prime to J. Oh, sorry, H is congruent to J.
Yeah, no, I mean the B and C. We kind of your additive condition.
Oh yes, sorry, B and C. Sorry, yeah. Yes.
Interesting.
It's an interesting one. And it's satisfy most of the property, like the general property which Ramanujan sum satisfy. I have said the orthogonality property, the multiplicative property, and I also find the value at primes. So there is not a closed formula in terms of like there might be some closed formula, but I couldn't find yet a closed formula in terms of Morpheus function, like the Ramanujan sums. There might be. And since it satisfies the orthogonality property, so we can write the arithmetical function as the series expansion of the sum. Using the orthogonality. Okay. Since the problem is to find the A, B, and C such that A upon R plus B upon S plus C upon T is an integer, so we just revisit the some properties of fractions. So we can write any integer as a prime product, and this product is a unique factorization for primes. If we take any integer A between 1 and Q, then we can write the fraction a upon q as the summation over prime divisor of q modulo 1, and this representation is unique. So for that, we first consider an integer which is q, capital Q sub p, which is equal to q divided by p to the power b sub p of q. And now we can see that for different q is like if we take the qp and qp prime, they are co-prime to each other. So by Euclidean algorithm, we can write a as the sum of qp's, capital qp's, and if we divide a by q, is this just sum over q over primes, such that prime divides q, xp over xp then p to the power minus b sub p of q. And for the unique representation, we take cp to be congruent to be xp modulo p sub p of.
This is like partial fractions for integers.
Yes, yes.
So nice, nice one.
And from here, so we consider the constant to be 0. P does not divide q, so we can take the summation over all primes, and we say that we consider a upon p as a fraction function, and the pole is the primes are the poles, and the order of the pole is the exponent of the prime. So the condition a upon r plus b upon s plus c upon t to be an integer converts to this constant times p for every prime p, p to the power minus v sub p r, v sub p s, v sub p of t is congruent to 0 mod. So now we need to find. And from here we can see that if any two of v sub p s, suppose v sub p s and v sub p of t both are 0, and this is not this is not 0, then it cannot be integer. The first consider condition, and the second one is if all are distinct, then it cannot be an integer. So so from there we conclude that if for some prime p, the exponent of prime that divides q, r, and s all are distinct, then the sum, this limit sum is 0. So we don't need to consider that case for the conjecture. Now we consider the next case to be square free. So the reason to be considered the square free case is okay. So here we have mu function, mu of q1, mu of q2, mu of qk. So if any of qi's is not square free, then this sum is 0. So it's sufficient to consider all qi's to be square free. So we consider the case when r, s, and t all are square free. So the v sub p of r, s, t can be 0, 1. And if we take the function curly k of r, s, t, k, h, j to be this exponential sum, we can see that this is the limit sum of the convolution of Ramanujan sums, because we are considering a upon r plus b upon s plus c upon t to be an integer, and a, r, b, s, and c, t to be co-prime. This comes from the Ramanujan convolution. So, so we need to find this sum, k sub r, s, t of k, h, j. For that, first we consider r, s, t to be square free, delta to be the GCD of r, s, and t, u is the GCD of r, s divided by delta, is the GCD of rt divided by delta, w to be GCD of st over delta. So we consider the same condition which comes from the Ramanujan sums, that A R, B S, and C T are co-primes, and this fraction A upon R plus B upon S plus C upon T is an integer. So, and R is T B square B. This implies R is delta times UV, S is delta times UW, T is delta times VW, and all delta U, VW are mutually common. Okay, so we can prove this theorem by this Venn diagram. So delta is the common region of R, S, and T. U is the common region of R and S divided by delta. So U is just region. Similarly, B is the common region of R and T divided by delta, and W is the common region of S and T divided by delta. Now, R, S, and T are square free. So suppose there is some prime here, like there is no common prime between S and T, and a prime here. So the exponent of that prime is 0 for S and 0 for T. And from our earlier condition, in that case, sum is 0. So every prime divisor of S and T, R, S, and T has to be in this common area. So this implies this. R is delta times U times V. S is delta times U times W. And T is V times delta times W. And this, from this Venn diagram, we can see all delta U, V, W are mutually common. Okay. So now using this result, the same we consider the same condition R is T to be square root. A is co-prime to R, B is co-prime to S, C is co-prime to T, and the fifth is basically A upon R plus B upon S plus C upon T is an integer. Then the convolution sum, the limit of convolution sum of Ramanujan sums can be written as a two-variable variant of Ramanujan sum, which is K delta H minus K, J minus K, times the Ramanujan sum, products of Ramanujan sum, which is C sub U of H minus J, C sub B of J minus K, C sub W of H minus K.
What is this first thing? This factor K delta.
Oh, okay. So this is the two variable variant of when we consider R is equal to S is equal to T. So we get the two variable variant.
So, is it like K delta delta? Is that what it should be, really? It's like the two variable one. I'm assuming there should be two subscripts or mine.
Can you go back to the definition?
Okay.
Oh yeah, I think it. Yeah.
It was K sub R of H and J. Oh yes, this is the definition. So it comes
I
from
see.
when we consider R is equal to S is equal to T.
I see.
Here we consider the R is, when we consider the case R is equal to S is equal to T, then we get this down and we call this to be K sub R of H and G. So the idea of proof is, so we know that this is the convolution sum of Ramanujan sums, this limit of convolution sums. And now we consider the R, S, and T to be square free. A is co-prime to R, B is co-prime to S, C is co-prime to T in the theorem, and A upon R plus B upon S plus C upon T is an integer. So from from this theorem, we have R is delta UV, S is delta UW, and T is delta VW, and delta U, VW are co-prime. So from here, we can write CR of n to be C delta n, CUN, CBN, because delta UN, delta UBN are co-prime. CS n to be C delta n, CUN, CWN, and CTN to be C delta N, CBN, CWN. And now we get two variable variant when R is equal to S is equal to T. When we substitute these three functions here, and first we consider the case when delta, 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 it will give us two variable variant because it comes from R is equal to S is equal to T. This U and U will give us this U component, and it comes from the Carmichael's result. Similarly, this V terms gives us this V result from the Carmichael, and W comes from the two W's using Carmichael result. So basically, that's why we can write this.
So in general, if you look at higher convolutions, are you going to keep pushing it down with some inductive method?
Okay, so higher convolution, we did the higher convolution, but by different method, because considering these cases is different, is very difficult to
Looks
consider.
like it's going to be.
Yes, it's very difficult. We did a result for higher convolution, but the method is very so ongoing. So this is the simple proof. Now we can give the heuristic proof of Ramanujan because we have the sum for this verificated. So like this is just recall the what is the Hardy Littlewood conjecture, and if we denote it by some function gamma, and BP is the size of the image of 0, H and J. So for simplicity, we are considering the first component to be first integer to be 0. So it's a image of the 0, H and J modulo a prime P.
This is the conjecture.
This is the conjecture. And heuristically, we can write the so this is gamma. Heuristically, we can write the conjecture gamma upon X is asymptotic to the summation over RS and T, mu R, mu S, mu T, P of R, P of X, P of T, and this we denote by this is the basically the convolution of Ramanujan divided by n. And we are considering the first term to be smooth. So from our previous result, we can write this sum in terms of two variable variant and the Ramanujan sum. So this will give us this sum is equal to this. Okay, so we need to show that this sum of series is basically equal to this constant, right? Now, and we know that in our theorem, delta U, V, W are mutually cofine. So we have to consider this mu square, which
Is it even clear this is a constant? What is the range of summation?
all are from 1 to infinity.
Yeah, so it's not even clear this is a constant.
So this is we have to show that this is equal to the constant.
Or maybe it is, you've got phi cubed, phi squared.
Yeah, I was gonna say, H and J are fixed, right? So.
Okay.
So we need to show that this is full function. And to ensure that delta U, V, W are mutually cofine, we consider this mu square. So for simplicity, we just defining to find a simpler formula of this function. We define the function f sub d of H and J, which is the convolution of these Ramanujan sums. And we can write this sum in a simpler form. So this is a convolution of Ramanujan sum. We can take the summation of the delta, convolution of delta and d, and then summation over times. So, since the Ramanujan sum is the multiplicative function of U, V, W.
Why do you get mu of n, not mu squared?
Mu of n.
Yeah, this is another complication.
So okay, so we have delta D is m. Delta is the product of U, V, W. So it's mu
Right
square.
on the outside, you have mu squared of n.
This is mu square m.
So you're some other mu of n comes in.
Yes, there might be some mu of m, one more mu of m from here. So, okay, so we have delta u v w. We can take one mu of m from there, and then we have mu square of delta, mu square of mu of u, mu of v, mu of w, which is mu of d times mu of delta. Okay. So this is the multiplicative function of p, this function f, and we show that this function is the multiplicative function of delta. This convolution is a multiplicative function. So the inner sum is multiplicative function, so we can write the series in terms of Euler product. Okay, and also because of this mu, we need to consider only primes. If like for prime power, it is 0. And so for primes, this inner sum is basically like when m is equal to 1, then m is equal to p, then we have c sub p of h and j. When it is equal to 1, then we have f sub p. And the inner sum is basically this Euler product. So we showed that this for a prime p, this c sub p of h and j is c sub p of h times c sub p of j. And when b plus c is not co-prime to prime p, then we have this c sub p of h minus j. And now we know that this Ramanujan sum is c sub p if p divides h. So basically, the c sub p of n is p of p if p divides n. Otherwise, it is equal to -1 if p does not divide, right? So we use that property, and we know that this sum, the constant depends on BP. The constant in, so we need to show that this series is equal to this constant, and this depends on BP. BP is the image of G of H and J mod P. So, okay, so first case, then BP is equal to 3. So it means, since we have 0 H and J, so P does not divide H, P does not divide J, and P does not divide H minus J. In that case, we use this Ramanujan sum and put here, and we get the required constant. If BP is equal to 2, then P either divides H or P divides J or P divides H minus J. In all three cases, we got the constant. And if BP is 1, then P divides H, P divides J, and P divides H minus J. So using this sum, we get the constant. So this is the heuristic proof of cable conjecture. So we can use
all of these can be written as product 1 minus b of b.
So we have the product of our primes, right?
Yeah, you evaluated it in that case, and so we're just saying that's equal to 1 minus b of
Yes.
times 1 minus 1.
1 minus 1 upon p to the power minus 2. So basically,
But you have p minus 1, can you go back to
okay, so I can, if we take the pq common here, take the p common from the numerator and p from the denominator, it will be 1 minus 3 upon p times 1 minus 1 upon p to the power minus 3. And the constant is same. 1 minus bp upon p times 1 minus 1 upon p to the power minus 3.
So that's where the p minus 1 is thing.
Since the series for von Neumann function is not absolutely convergent, so the proof is heuristic. Suppose we have a convergent series, so we can find the convolution, like absolutely convolution of the function. And the Jordan-Torsion, if you consider the Jordan-Torsion function, it has the convergent series in terms of convergent sums. So basically, Jordan-Torsion function is n to the power alpha, p divides n, 1 minus p to the power alpha. And alpha is a fixed number greater than equal to 1.
So you use now for bigger now.
If alpha is 1, then it is a polar torsion function. So for that, we have the convolution of p alpha n upon n to the power alpha, p alpha n plus h upon n plus h to the power alpha, p alpha n plus j upon n plus j to the power alpha is congruent to alpha times this constant. And this constant is also depends on BP.
So
BP
constant is what?
depends on BP.
Oh,
So
yeah.
we are dividing the case when BP is 1, BP is 2, BP is 3. Okay. And BP is the distinct algebraic classes of G words in G. So Ramanujan itself gave in his first initial paper the series expansion of Jordan-Torsion function, which is 1 upon zeta of alpha plus 1 summation over r mu r divided by p alpha plus 1 r cr. And since in this we have this pr, so we can use our like square field. And using that, the convolution is same like this series. Now we have this summation. After substituting this summation, we can write the series in terms of u delta v w, and similarly considering this to be a function of d over the convolution and showing that this is a multiplicative function, and same procedure we get the result like the constant figure. And this is for p alpha n over n to the power alpha. If we use the partial summation from the theorem, we can get the convolution of Jordan-Torsion function, which is the order of x to the power 3 alpha plus 1. And the constant comes 3 alpha from the.
So you're doing this instead of lambda, you put 3 out. That's it, right?
So no. So in this result we have alpha.
I understand, but
When we use the partial summation,
to avoid the convergence issue, you're using 3 sub alpha.
yes.
Because lambda you couldn't.
Yeah, so this gives the heuristic, but this is the convergence, so we use.
This is not heuristic now. This
This is not
So
heuristic.
here,
This is not heuristic.
although, I mean, there's no, like, this is not a sum over primes though, like it was before, right? I think that's also the other change.
1 second. Okay, so this is the sum over all primes. So like in that case, if we divide the like.
Sorry, I meant the sum on the left-hand side, not like not the product, but the, like, yeah,
It's
it's
not prime detecting.
yeah, exactly, it's no longer a prime detecting sum, yeah. But that's fine, I just wanted to like that clarify that I'm understanding it correctly.
So using partial summation, we can get the combination. So these are the results in this paper. And for the case k equal to 2 is in the Carrier and Padma's paper. And this is the Ramanujan's initial paper on the certain trigonometric series, in which he gives the series expansion of convolutions.